Right. Well, I think it's 12 o'clock, just a minute past. I know it's a smaller group than normal, but I guess the title may have dissuaded some. Um, I think most people on this call will have been part of our earlier series of webinars from Stiebel Eltron and presented by the Net Zero Hub. So I don't think I need to go through and repeat who we are. It might be worthwhile just reflecting briefly on where this webinar fits within our series. We've done already the brief introduction into how heat pumps work, how to understand them, the planning and specification of heat pump systems. And now this webinar is dedicated to commercial heat pump systems. The intention really is to give people an opportunity for Matt at Stiebel Eltron to walk through a presentation on the aspects of commercial heat pump systems that are useful, and then to allow some time for Q&A afterwards. So that would then bring us to our penultimate webinar in a couple of weeks on maintenance and repair, and then we'll be having a summary on site for those able to get down to their Bromborough site. So without further ado, I think I'll hand over to Matt. We all know Matt. He's led us through the previous series. Not much more to say, Matt. Shall I just hand over straight to you?
Yeah, that's perfect. Thank you very much. So good afternoon. In this session, we're going to look at commercial heat pumps. There are a couple of aspects that we're going to cover. So we're going to look at some tips on correctly sizing the heat pump for commercial systems. We will also look at ways to find the best solution. This is a crucial aspect of any design feature for any heat pump system. Quite an interesting look at domestic hot water demand. Do we need the heat pump to complete domestic hot water cycles, or can we use other products and other solutions in place? Is cooling required? Now, most people understand cooling through air conditioning units, but heat pumps can cool as well. And then we'll have a quick look at BMS and Smart features. I've kept this as an introduction to BMS and heat pumps. We'll look at this more in the Q&A session after the presentation. So we'll look at some tips on correctly sizing the heat pump. So some key points to take away when we're looking to size a heat pump for a commercial property. First of all, we need to look at the building type and the proposed use of the building. An office building which has been renovated from a retrofit property from the early 1930s, 1940s, or for example, the old mill style buildings that have been renovated from the late 1800s will not only have a greater heat loss requirement than a modern building, but there are other aspects that you will need to look at, such as ventilation. If most of the building is solid wall, with or without insulation, it's relatively easy to complete a heat loss calculation. And I've purposely used an AI generated image on the slide we can see on the screen, because in most modern buildings, we want a light, airy, open feel, which normally means a large amount of glass. Now, glass has a higher heat loss than brick, concrete, all of the normal building materials that we use. But on the other aspect, it has a greater solar gain. So if the commercial property consists mostly of glass, we will find that it is difficult or can be difficult or challenging to heat in the heating season, and then proposes another problem in summer or warmer months, which is the solar gain overheats the property. So we then have two problems where too cold in winter and too hot in summer. And it's quite a challenge to undertake. We also need to look at how the building is being used. So a standard office block may have 100 offices, but at any day in the week, only 50, 60, 70% of those offices may actually only be occupied. We would still need to specify the heat pump size for the full capacity of the working load of the building. So all, 100 offices in use at the same time. Same for domestic hot water. We need to keep in the redundancy. If we look at gyms, sports halls, any area where we have mixed use, so that could be a sports area with showers, but there could be offices above, then we'd need to see the best solution. Now, it could be that an open sports hall, 3.5 meter ceiling height with gas blowers, and then 50 to 60 square meters of office area. Well, it's probably best through what we call a split system. So one air source heat pump system or ground source heat pump system heats and delivers hot water to the offices. And then we have a second proposed system for the sports hall or the area that is going to be in frequent use. And that's because we have two completely different build characteristics. We also look at scenarios such as cricket clubs, rugby clubs, football stadiums, venues where it will be once or twice they are used per week. But when they are used, you could see 20 or 30 people coming in for domestic hot water use. So each commercial property should be taken independently. We also need to look at the heat pump location. So if we look at the office block we have on the screen, it's very limited place or area to install air source heat pumps. We could potentially have them around the back of the building in loading bays or potentially on the roof, which then leads to issues of trying to get the heat pumps up there, maintenance, service and repair. If this was a more rural application, we may find fields or grass areas around the commercial building. That could then become a ground source heat pump rather than an air source heat pump. But we'd still need to ensure that the access to the plant room is sufficient. It may be a remote plant room, which is a building just behind the commercial property, designated solely for the purpose of housing the equipment for the heating system, the hot water, and potentially the ventilation. We also need to consider which is better, ground or air source heat pumps, and it will all depend on the application. If you have an area where you can use boreholes, which previously covered in our previous webinars, they are the collectors which go directly down into the ground, so vertical rather than across a field. You can fit more in a smaller area. So ground source would have a better efficiency and be applicable for that compared to having large or multiple air source heat pump units. So finding the best solution. When we look at different applications, for example, commercial offices, the question I always ask is, what is the heat emitter type? This will all depend on the system design. If we have radiators which have been correctly sized for the rooms on a wet system, then we can look at having air source or ground source heat pumps with a suitable flow temperature for the radiators. It could be that the office blocks or the offices are using underfloor heating, which is more common. Again, we can still focus on using an air or ground source heating system. We will need to reduce the flow temperature, which in turn will increase the efficiency, and we may not need as much storage for the heating system compared to radiators, but we'll also need more space to be able to blend that temperature down to the correct temperature for the underfloor, depending on the outside air temperature. If the property has existing heat emitters, we then need to look at what is currently installed. Is it suitable for the new application? So flow temperatures. And I've purposely put cast iron radiators on there, because if you try to supply a cast iron radiator at a 45-degree flow temperature, it wouldn't have the same performance or output that it would if it was supplied at 60 or 65 degrees. Also, you will find that pre-existing cast iron radiators have probably started to slightly corrode inside, which means inside the heating system you will find debris, dirt, potentially flakes of cast iron, the metal coming off the radiators. Now, if we introduce a new heater or heating system to this, we would need to flush the system out multiple times to try and clean the system out. It is very, very difficult to get every last aspect of debris out of the system because there are small joints, turns and bends in the pipework, and then flow restrictions inside the cast iron radiators. So in this application, we may have a split system. The cast iron radiators and existing existing heat emitters stay on one circuit, which is separated with a plate heat exchanger connected to our heating circuit, allowing the heat to transfer through, but the fluid is indirect. It will never have any direct contact. Or potentially upgrading to K1, K2 radiators. What we find is most of the radiators on site may need upgrading, but you will find that larger radiators may be suitable for different rooms, so you can transport them into or transfer them into different areas. We also look at cooling in offices. We all like to achieve a comfortable temperature throughout summer and winter. When we're looking at cooling, we cannot cool through conventional radiators, either K1, K2, K3 or cast radiators. It's normally done through underfloor heating or fan coil units. Multiple occupancy properties. I've factored these in with commercial applications and commercial buildings because they follow the same path. When we're looking to design a heating system for a multiple occupancy property, such as flats, we would need to complete heat loss calcs for each room or each flat to give us the determined heat loss for each flat, and then look at how to supply heating and hot water to these independent flats. So we would class this as a district heating example. And you would normally find a very large cylinder in the plant room for the underfloor or the radiators, and then a very large cylinder for the domestic hot water. And the heating cylinder or buffer cylinder will supply each flat. And the question always is proposed, well, how do we know how much each person in the flat has used in the way of energy? Well, there are components called heat interface units, or HIUs for the abbreviation. And inside a heat interface unit, you will find a heat meter, a second heat source, so normally an instantaneous hot water heater, and temperature sensors. And each flat would have a heat interface unit, and it would draw off the large cylinder, the buffer cylinder for the heating, and that would monitor the energy usage for heating and also hot water for each independent flat, allowing each property to be built independently. We also look at what if, in case of emergency scenario, should we have an emergency heat source? In my opinion, I would always recommend having an emergency backup. It's better to have it and not need it than not install it and then fall foul and need it. Because if you imagine you have a property that's a block of flats with 8 to 12 tenants, and there has been a failure, there has been a breakdown, you now have 8 to 12 tenants currently in need of heating and hot water. If there's an emergency system, this can be initiated and there is minimal disruption to the tenants. The work can be completed and the heat pump system is back up online and more efficient than that second heat source. You may also find with pre-existing multiple occupancy properties or office blocks, commercial properties, they may have gas or oil boilers already installed. Now we can create what is called a bivalent system. This means we cater for the majority or all of the load for the property, and we leave the gas or oil boiler in as the backup. It also means on exceptionally cold days, as we can see in the UK at the moment with the various storms and snow, that if the temperature does drop far below the average temperature for the area, we can send a signal to call on this second heat source and provide an additional level of input and energy to the property, ensuring that the property is never cold. So we've looked at new and retrofit commercial properties and multiple occupancy properties. Let's have a look at what I call myth busting. Grade 1 or 2 listed properties, old housing stock or old commercial buildings such as those 1800s mill style properties. Well, the question we normally get asked is, will a heat pump work? The answer is yes. You will see a lovely 18th, 19th century property on the screen. This isn't AI generated. This is a property called Plasnoeth in North Wales, just off the Menai Straits. This currently features our heat pumps, our ground source heat pumps, and we're extracting the water from the Menai Straits and using that as our environmental source. Now, originally this property had oil boilers. And we said, well, what's the lowest flow temperature that you can achieve in this property to ensure the property is warm and it's comfortable and it's usable? And the temperature was managed, or we able to get it down to 45 degrees, which is perfect for ground source or air source heat pumps. And then the installation took place, the oil was removed, and the ground source heat pumps were installed, and it's saved a huge amount on running costs, but also we've been able to take a grade listed building, install renewable technology, and if we look at the picture, we cannot tell if it's fossil fuel or ground source or renewable technology on this property. So this process transfers to any grade 1 or 2 listed building that you will find in National Trust, English Heritage, any site across the UK. We need to determine the lowest flow temperature that we can achieve to maintain what we call a comfort heat or comfort level of heat in the property. And this will protect all of the antiques, upholstery, and if it is used for example, a museum or it's an event property, so you can go and walk around, you can see the building and the grounds, then it's comfortable for anyone attending. Once that's been established, we need to look at the heat emitter type. Is it cast iron radiators? Well, knowing the property, it probably will be. We don't want that system to interact with our new heating system, so we'll use a plate heat exchanger to separate those two heating fluids, effectively, the heating water. Then we'll look at domestic hot water and find a solution for that. Now, if we're going to see multiple bathrooms and kitchens used, we'll propose using a domestic hot water cylinder with an air or ground source heat pump to increase the efficiency and again reduce the carbon output for the property. Should we install a second heat source? Yes, is the easiest answer. If it's going to be used for public events, personal use, whichever, we should always have that second heat source there. The property has quite a large amount of value in the way of what's been installed, what's in there, and its historical value. So yes, we want to maintain that moving forwards. There are a lot of restrictions with grade listed buildings. Will it affect the appearance? Where will it be installed? Is it visible from the outside? Will any of the architecture or existing components inside the property change? Are we trying to run new pipework to various radiators? All of these aspects must be addressed. And normally what we find is air source heat pumps can be installed with a cover around them so they are not visible. We've had some cases where they've been vinyl wrapped to match the exterior brickwork and design of the building, or they could be installed in areas of the roof where it's dropped, it's lowered, and it's not visible from the outside. And ground source heat pumps are normally the easiest because they can go inside an existing plant room, and the ground collectors will go out into the ground a metre to a metre and a half below, completely hidden in this example, and it's not visible. In the Plasnow example, because it's extracting from the Menai Straits, there's a floating pontoon which rises and falls with the tide, and that's not visible as well. Domestic hot water demand. So I've put two examples on the next two slides. The first example, should we use an air source or ground source heat pump for domestic hot water in a commercial property that only has one kitchen sink, 3 hand wash basins, and 1 sink in a cleaning area? The maximum volume of water used per day on a worst case scenario would be 100 litres. In my honest opinion, the answer is no, because we would need a 200 to 300 litre cylinder to normally cater for the coil size that we need. So we would have an exceptionally large cylinder when our average usage on a worst case scenario is only 100 litres per day. There are, for example, our 200 litre stainless steel cylinders, which are small and compact and will give you a mixed water volume of 312 litres, but again, it's still quite a large amount. You also must take into consideration how far away each draw-off point, so each sink or tap or shower, is from the cylinder. If these 5 draw-off points are over 5 floors, you would need to run the pipework from the hot water cylinder to the top floor, to the 4th, 3rd, 2nd, and ground floor. And due to the distance, you would then need what's called a domestic hot water secondary circulation circuit or system, which is constantly circulating the water around these 5 draw-off points. All this is doing during the working hours of the day is removing that heat, that energy we've stored in the domestic hot water cylinder, just to ensure that if someone does switch on the tap, they will have instant hot water. There are other products on the market, and I've put 2 of our products on the slide. To the left, we have an instantaneous hot water heater. The easiest way to understand these, most of us have them in our own property. It's a bit like an electric shower. The cold feed goes in on one side. There are elements inside that heat the water up to the set temperature on the controller, and then the hot water comes out on the left-hand side and is delivered to the hand wash basin, the shower, the sink. Depending on the size of the instantaneous hot water heater, it can either supply a single basin or it could supply 2 to 3 showers in a commercial gym. But these are direct and they can be installed within a close vicinity of the draw-off point. So this makes it easier to not only install, service and commission, but we're not seeing as much pipework running through the property, and we don't need secondary circulation domestic hot water systems. On the right-hand side, we have the conventional undersink or oversing 5 to 15 litre storage cylinder, which can supply 1 or 2 sinks. Again, it's direct, it's point of use, it's very, very minimal draw, very low heat loss, very low power consumption for the amount of water that will be used throughout the working day. So let's look at the same property, or same commercial property, and we'll now say that this property has 1 kitchen sink, 7 hand wash basins, 2 cleaning areas with a single sink each and 9 showers. It could be a sports facility, it could be a gym. Now we're going to use, on the worst case scenario, 800 litres of water per day. Now this would be a great example for an air source or ground source heat pump to feed, because we've got a large hot water demand. If we were to feed this with electric immersions, we could potentially need 12 to 24 kilowatts to supply this hot water cylinder, which would in turn be not very cost efficient. Electric immersion heaters are what we call 1 for 1. Every 1 kilowatt spent is 1 kilowatt delivered to the cylinder. So you could be using potentially 24 kilowatts per hour to heat a cylinder. And we can maintain a high level of efficiency with an air source or ground source heat pump. In some cases with commercial ground source heat pumps, especially considering ours, we have a feature called hot gas, and it allows us to feed the domestic hot water cylinder with energy, with heat, and reheat that cylinder whilst we are still heating the property. So we're operating in 2 modes at the same time. Is cooling required? So we'll run through this one. I've put some key points up. Does the commercial building have a large glazed area which allows additional solar gain? If you have a large area that is a large amount of glass, you will see the temperature increase in the warmer months, even spring and autumn, due to the solar gain. You can install air conditioning units for these areas. However, when you compare it to an air source or ground source heat pump, to add air conditioning on to your existing renewable heating package, you've now got twice the component cost, twice the servicing cost, twice the maintenance and breakdown cost. You've also got 2 control systems, which if you're manually operating these, you will find there's a crossover where one person might want the room at 18 degrees and someone would like it at 21. So someone will switch the air conditioning on while someone switches the heating on. So you've now got a battle of the forces effectively taking place in this area. You've got the heating system trying to add heat into the room while the AC is trying to cool the room. If you have a BMS system, a building management system, you've then got twice the load, twice the output, and twice the programming to get these systems to work together. In glazed areas, you may need as much as 200 watts per square meter cooling energy to cool this area. So it's quite a large amount compared to a normal heating circuit where you may only need 50 watts per square meter to heat the room. Then we look at the actual building type. Is it a sports area? Is it the gym? Are there sports halls or training areas? Do we need to keep these areas cool and potentially heat other areas such as offices, potentially changing rooms, shower areas? Do we need to keep these warm whilst we're cooling? If this is the case, then we can look at a simultaneous heating and cooling system with an air source or ground source heat pump. Do we need to keep certain rooms cool, such as server rooms? Well, yes. Server rooms should never go above a certain temperature throughout any moment of the heating season. So we need to keep them at a fairly stable temperature because the heat generated from these servers overheats the room quite quickly. So how can we cool? So we've got a very small diagram on the screen and it's cooling through underfloor. Now, if we have underfloor heating and the spacing is correct and the flow and return pipework is insulated, then yes, we can cool this room. And effectively, all we are doing is taking the thermal mass out of the walls, the floor, the screed, and anything in the room, and putting it into a colder flow temperature through the underfloor collectors, and taking the energy away from the room. This will reduce the room temperature by 3 to 4 degrees, depending on the room. We can cool through fan coil convection, which is a fan-assisted radiator, which is a bit more effective. So there's multiple options. Can we cool and heat simultaneously? Yes. We've seen this proposed in hotels where they may have a bar area which needs to stay cool, still provide heating and hot water for the rooms and the lobbies, the foyers, and the reception areas. It can be done at the same time with our ground source heat pump systems. So cooling methods. Large areas can be cooled through underfloor. It's one of the most effective ways, but it is determined by the floor covering. If you have a very high TOG rated carpet, then the cooling may not be as effective because we've got to go through that thermal barrier. If it is very thin carpet, or it's tiles, it's laminate, it's wood, then it is highly effective. When I say it's cool, if you were to take your shoes off and put your feet on the floor, it wouldn't feel like standing on a cold tiled floor in the peak of the heating season in an unheated room. It is more of a cool ambient temperature. Again, we addressed this before, but cooling can require more energy than heating. So if the cooling output of the underfloor isn't sufficient to cool that room, we can introduce fan coil units, which will blow cold air around the rooms. To put it in comparison for temperatures, the underfloor will only be supplied at 17 degrees flow temperature with humidity sensors to ensure there's no humidity buildup and there's no condensation. Fan coil heaters, and when they're operating in cooling mode, can be supplied at 7 degrees, so exceptionally cold. They will normally have a condensate tray to catch any condensate buildup, but they can supply up to as low as 7 degree temperature in the room to bring that temperature down. Now, when we compare fan coils on the floor and a heat pump system compared to AC, not only is the equipment cost more favoured towards the air source or ground source heat pump system in the way of costs, but also the longevity, service and maintenance costs are a lot cheaper than rather than having two systems. Now, when it comes to sports areas, large halls, you'll normally find what's called downdraft heaters or gas blower heaters, which are blowing hot air around the room. When we're looking to heat or cool a commercial property through this, it may not be as efficient because we're trying to supply it at higher temperatures. It can still be done. And what we may find is we may need some more blower heaters to be installed or a supplementary heat source, for example, additional radiators. Now we can heat and cool through MVHR, mechanical ventilation heat recovery. And this works in the same process as the downdraft heaters. We will have plate heat exchangers that cool or heat the air. And in doing so, rather than bringing in 25-degree warm air from outside in the summer period or 6-degree air temperature in the winter, we will add or reduce any heat or cool the air before it's applied to the rooms. This is what I would class as a supplementary heating or cooling method. If you had cooling through underfloor with cooling through the MVHR, you will see a better benefit rather than just cooling through the MVHR on its own. So BMS, integration and smart features. Our heat pumps, among others on the market, can communicate with BMS systems. It will either be through a wired connection, which is RTU, or TCP/IP, which is wireless. I would always say look at the control parameters. Try and reach out to the manufacturer to see what the control parameters or what's the best recommended control parameters to use for the system, because some can be misguiding in how they're described. The BMS control system is a simple on or off program. It doesn't understand the design and running methods and processes of an air source or ground source heat pump. So I always try and leave the BMS system to be an input rather than a main control feature, allowing the heat pump to ramp up to a higher output and reduce down, manage its own flow temperatures, and ensure that it is efficient. We can't treat them like a gas boiler. We can ensure that the heat curves, the domestic hot water temperatures are achieved through BMS. We can have fault outputs. We can also switch the heat pumps off on demand through a BMS system. So if you've got a property where the connected load isn't as high as we would like, and if all of the computers, servers, everything are on at the same time, we may need to switch one heat pump off. A BMS system can do that. I am just keeping an eye on the time, and we only have around 20 minutes left for the Q&A session. So I will wrap the presentation up there, and we'll have a quick Q&A session.
Right, thanks, Matt. That's much appreciated. Thank you again for an informative little walk through there. I wasn't aware we were going to get quite into the details of cooling, but it's a fair comment. We probably spend a huge amount on HVAC in commercial properties. For those of you with questions, do you want to drop them into chat? I can pick them up from there and then relay them through to Matt. Matt, at the start of your presentation, you were talking about elderly properties. You had your grade 1, grade 2 listed building there, and bits of rust in the system, and you said, well, that's going to require a separate circuit. Surely things like just magnetic separation filters and things like that would be normal where we've got iron radiators and things like that.
It can help, but the filters and the flushing is only as good as the debris we can get out of the system. So if we find there is a large amount of debris built up in the system, it is easier to separate it with a plate heat exchanger, which then protects the heat pump, the heat exchanger inside the heat pump. Like anything, if you have a large chunk of iron that's separated from the radiator and it's rusted, that could block an orifice, and then through pressure that breaks down. But there are some cases where it doesn't actually break down, it stays that size, and that could then cause a blockage. So when you have that separation, it makes it easier for any breakdowns and servicing calls, because there's still heat being delivered to the system. It may not be as much, but then we can address that on the old side of the system.
Okay, that's fair. I've got one more question, and then we'll move to a few that are dropping into chat. Direct electric heating. So it seemed to be the example you gave was the small commercial property using 100 litres of water. You go, right, we'll go for direct electric heating there. And then as the scale goes up, we get to 800-900 litres, and there's a case of there that a heat pump solution would work. Where's the cutoff point? Where do we start saying actually the volume where we're starting to move towards a heat pump being the right tool, and at lower volumes direct electric heating where we can save and not have to heat all the water in extensive pipework runs and things like that? Where's that cutoff point?
So if I use two examples, if we had a small car dealership that had 2 bathrooms, some employee wash basins for the technicians in the service bay area, and maybe 10 to 12 customers per day, this would be a small point of use scenario, because it would be infrequent use. You may find the hand wash basins are used 6 to 8 times a day, and it could just be a kitchen sink for adding water to the kettle, washing cups. If we look at a small office block with 30 to 40 people in the office block, and we'll say 15 to 20% work from home 2 days of the week, and the remaining 3 days of the week we have the full occupancy of 30 to 40, and we had the same amount of hand wash basins, so we'll say 8 altogether, then I would look to put a cylinder in to be fed by the air source heat pump, because we have a higher change of hot water. There's going to be more chances that hand wash basin or those hand wash basins are used per day, and it would be more cost effective to heat the cylinder up to 50, 55, 60 degrees, ensuring the cylinder has a low thermal, a very small heat loss. If the op is closed at 5 o'clock and the cylinder was at 50 degrees, you would find the next morning the cylinder could be at 48. So you haven't lost much in the way of heating it up. It all really depends on, I would say, number of people, usage, and volume of water consumed. So if it's going to be 20 or 10 people, and at any given time, it's small usage, maybe 50 to 100 litres, I would probably say use point of use.
Right. Okay, that's fair. Gives us a rough idea. Moving to Q&A questions coming through. Cost per kilowatt. What's the sort of cost per kilowatt for the capital costs of install that you see? So, rule of thumb here, and I accept you might need to give us a range there, but per kilowatt, what does it say? And this assumes it's linear. It may not be linear.
Oh yeah, if it's a new build, it would make it a lot easier because you've got free reign of running the pipe work. If it's a retrofit, it could be more difficult. I normally use the figure between, I would say, potentially £2,000 to £2,500 per kilowatt for air source, and maybe 3,500 to 4,000 for ground source on commercial application. Now this is a rough rule of thumb. Each will vary depending on the property and the design. It also depends on the system as well, because, great example, if you had a property that had an 80 kilowatt heat demand, you could supply it with one 80 kilowatt unit or two 40 kilowatt units. In my opinion, I would opt for two, not for price, not for value, not because the salesperson would earn more money, quite simply for efficiency and repayment and the payback, because you'll have two units operating at a lower temperature and lower output compared to one working a lot harder to cover the load. So as you can imagine, between two versus one, there would be a cost difference.
Okay. Where do you think people should, or when people are discussing with their installer about the costs of a solution, they're weighing up two versus one, what sort of the key parameters to look at be? Because in many cases the person is going to say, you tell me what you recommend and we'll go and install it, but how should a buyer sort of look at that trade-off of two versus one? Because that's certainly going to be a feature for larger properties and commercial sites.
It is. I would look at the efficiency and also the heat loss of the property during the majority of the heating hours. As we covered in a previous webinar, we only see around a third of our heat requirements at our design temperature. 2/3 is between around 3 to 9 degrees. If you can have the system that's far more efficient between 3 to 9 degrees, which could be two units it will be 2 units rather than one, that will give you a far better payback and better efficiency and higher COP and output compared to one unit. That's where I would look and focus, because it's quite easy to take the cheaper initial cost and have one large unit, but you'll find during that heating season, that 2/3 of the heating season, your single unit could be operating at 60% or 50% capacity, or maybe 70%, whereas two units would be operating at 30%. And it's a lot more efficient to do. And the more efficient the output is, the less you use to run that compressor, the less it's going to cost you. So that's how I would look at it.
Next question is up from Joanne. Now, Joanne, jump in if I'm going to garble your question, but if you've got a plated exchange with old radiators, and I think what we mean here is, are we effectively being inefficient by having an efficient heat generation system being pushed through inefficient radiators? I guess there's a trade-off where eventually you say, actually, just take out the old radiators.
Joanne, you are completely correct. I like the expression robbing Peter to pay Paul. Anytime you were to add a plate heat exchanger or another transfer station, as I call it, onto a system, you are effectively adding an additional heat loss or inefficiency into that system. Now, there are some scenarios where inevitably we cannot change the radiators. For example, the grade 1 or 2 listed buildings where they have to stay in there, or a suitable, modern, appropriate radiator can be sourced. If they have to stay in there and we have to separate the system, then unfortunately we all have to make the compromise, which is we've got to sacrifice some efficiency for the building to retain its natural original characteristics. On the other hand, if we can look to source modern cast iron radiators with a better heat output that will be suitable and brand new, then once we flush the system and new cast iron radiators are installed, we can connect directly onto that system. But the last thing we want to do is allow any debris to come through back into the heat pump and back into the heat exchangers, because they're connected to the refrigeration circuit. And rather than a plate heat exchanger on a wet system, a radiator system or a heating system, they are a bit more difficult to change. So we want to keep any debris, any muck, any build-up away from the heat pump, which is where that plate comes in. But if we have the ability to remove those old cast iron radiators and install new ones, it's the best approach. If we are stuck and must retain with what we already have, then we'd integrate that plate heat exchanger.
Okay. And then Jamie, coming across Jaeger, who've got effectively cooling from their radiators. And is this simply, well, first of all, have you come across Jaeger? And is this essentially taking your idea of putting low temperature water into the underfloor and now instead also pushing it through radiators?
It's funny you mentioned Jaeger, because Jaeger are one that we would normally recommend or we've seen used for our equipment. Yes, fan coil units are brilliant. They not only just for cooling but for heating, because they're blowing or moving the air around the room. It gives you a lot warmer feel, and especially in the heating or the summer season when we're trying to cool, because we have the airflow, we feel a lot cooler. And the best way to explain it, if you're out on a summer's day and it's 25 degrees and there is 0 breeze and you're stood in the sun, it's quite uncomfortable. You're very hot. If there's a 5 or 7 mile per hour breeze on that 25-degree summer's day, you feel cooler. And that's exactly how these fan coils operate. They take the heat out of the room, they cool it down, it's blowing cooler air. But the bonus is, the benefit, you can supply them at such a low flow temperature, 7 degrees, that it's a lot more effective than underfloor. It's a lot more reactive, I should say, because underfloor has to remove the energy first before you feel the cooling effect. The fan coil units are blowing that cold air around almost instantly.
Right. And so essentially we have a fan. So I don't know the system, but does that mean that we've just got a fan effectively moving air over a radiator and helping exactly as you do with a hot radiator, instead of increasing the airflow over the heat source, we're now moving the air over the heat sink.
Exactly that.
Okay.
Yes. Yeah.
Right. And then a question from Joanne: does the Jaeger system separate the cold and heat as a variation in temperature creates wear or inefficiency? How does it work? So can you do that question, Matt?
I can. I mean, Joanne, please pop in the chat if I'm wrong for my understanding. But what you'll normally find is there will be heating or cooling. You can have simultaneous heating or cooling. The heating and cooling system normally doesn't need a separate amount of pipework or flowing returns. They come from the same area, and it can be changed with valves. And what you'll find is when the room needs cooling, the fan coil will blow the cold air around. That'll be, sorry, I'll start from the beginning. The air source or ground source heat pump will either heat a buffer cylinder or chill a buffer cylinder. And then the heat emitter will extract from either the hot buffer or the cool buffer. Now, the fan coil system can extract from the hot or the cold, and it will be almost simultaneous. It would just transfer the heat through. Inside every heat emitter, there will be a programmer, and that will determine the room temperature. So if, for example, it's a summer's day and you're trying to cool a room, then what you will find is the fan coil unit will understand the room needs to be cooled. It's at 25 degrees. We need to get to the 21. The pump switches on, pulls the cold water from the cold buffer to the fan coil unit, blows the cold air around the room. Once the room thermostat detects it's 21, it switches off. And then in winter, it falls below the set point. Hot water or warm water comes from the buffer to the fan coil and then heats the room up. The big misconception that we have between AC cooling and heat pump cooling is with AC cooling, we just put it to the lowest temperature possible and go, right, okay, it'll cool the room down really, really quick. And then we have to switch it off, and then we need to put heat back in the room because it's too cold. With an air source or ground source heat pump heating and cooling system, it's using that weather compensated trend. It's always ensuring that it's constantly cooling or constantly heating to manage that room temperature. So you don't normally need to switch between hot or cold. The easiest trick for anyone driving home, probably a bit brave in this weather, but when you get in your car, pop your AC on, turn it down to the lowest it'll go, 16 degrees, and drive for 5 minutes, and you'll feel really, really uncomfortable and cold. And then again, have it at 20 degrees or 21 with the AC on, and what you'll find is it'll be a nice stable climate. It'll be constant, and that's how the heat pump delivers the heating and cooling energy. So we find that we don't need to switch between hot and cold so much with the heat or cooling emitters.
And Matt, in terms of what's actually happening inside the heat pump, we've got a compressor and an expander valve. And if you stand next to a heat pump in winter, they're blowing out cold air as they extract heat from the air. In summer, if we're on cooling, then clearly my understanding would be it's running in reverse, and that heat pump unit will be blowing out hot air exactly as an air conditioning unit goes. But if we want to oscillate between heating and cooling, we've got this large water buffer tank sitting there that we would then need to heat or cool before we can actually start providing a temperature change to the radiators or the underfloor heating.
Yes. So in that scenario, if it was what we call simultaneous heating and cooling, we would have two cylinders. One sole purpose is to be a cool buffer or a chilled buffer, and the one to be a heating buffer. So we can swap between the heating and cooling buffer to ensure that we have the store of either energy, hot or cold.
Which could be quite expensive because that means two buffers, and you probably wouldn't be using one of them for half of the year.
Yes, so it all depends on the application. So if you've got a gym, a sports arena that needs heating and cooling, and you've got the area, I would say go for ground source because that can use the energy from the ground to cool the buffer rather than using the heat pump. So that's offsetting the cooling costs. And then if it's an office that's well insulated, I would have heating and cooling seasonal rather than simultaneous, quite simply because the heat pump will be able to manage those room temperatures efficiently.
Yeah, that's fair. Okay, we're coming up towards the top of the hour. Can I see if there are any other questions? Sort of a last call for questions, and see what we've got coming through. The BMS system that you've suggested there, Matt, was where you keep the BMS separate from the heat pump. You let the heat pump manage itself, and the BMS effectively cools off my understanding was the BMS would then call off from the water tank. How do we integrate the whole system to take advantage maybe of variable electricity pricing and things like that? How's that managed, or is that very specific software?
So that could be built into the heat pump programmer. It could also be built into the BMS system. Again, I can't speak for the manufacturers, but for ourselves, we've got inputs to increase the output of the heat pump to switch it off. So if it's a cheap tariff, we can increase it and benefit from it. If it's an expensive tariff or we don't need the heat pump to run, the BMS can switch it off. We've got solar PV integration. So again, same scenario, we can deliver the energy as and where we need. And this can all be done through the BMS portal to send the code to the heat pump and say, okay, it's now 5 o'clock, everyone's gone home, you don't need to run, and also we're now on an expensive tariff, but at 8 p.m. we're on a cheap tariff. You need to start the heat pump, or the heat pump needs to start there and run for 6 hours and put the heat in. So it can be done through the BMS panel, it can be done through the controller as well. And as long as you've got the corresponding codes, it isn't a problem.
Right. Excellent. Okay, that brings us to the top of the hour. The next session in a few weeks is maintenance and repair on heat pump systems. Again, we'll be joined by Matt to talk us through that. Namita will be sending out the invitations to everybody. And yeah, I wish everybody a very, very happy rest of the day, and see you all again in a couple of weeks.